This lecture is a replacement for the lecture that we were scheduled to have on the 2nd of November. My sincere apologies for not being able to make it to class on that day. I was planning to cover partitioners and combiners in that class. This is section 2.4 from our MapReduce book. The slides for the same have already been uploaded, and I hope that you have had an opportunity to go through them already. We will also need to talk about the bigram code, which is a sample code for your project at some point. You will also be given a separate video recording for helping you understand the bigram code and modifying it to write a trigram code for your project. Please expect this also to be circulated shortly. That said, let's get started. The material, as I mentioned, is from section 2.4 of the MapReduce book. We've talked before about how the mapper and reducer functions work in a Hadoop environment. To recall that first, the job tracker partitions up the job and sends it to the appropriate mappers. The mappers take an input, the key value pairs, and generate the intermediate key value space. Then this intermediate key value space, the key space is actually further partitioned so that the reduced tasks get their work. We've never quite talked about how the actual transfer of the intermediate key value pairs takes place between the mapper output and gets sent to the reducer. In this lecture, we are going to investigate that aspect of the job tracker work in terms of partitioning the intermediate key space a bit more in detail. So intermediate key value pairs must be grouped by key, and these are large distributed sort operations involving all the nodes that executed the map tasks. In the lingo of MapReduce operations, this is known as a shuffle and sort phase. In general, a partitioner is, and you will soon learn also about a combiner, are two additional paradigms for the MapReduce programming environment. Partitioners are responsible for dividing up the intermediate key space and assigning these intermediate key value pairs to the reducers. So in fact, they are one of the primary tasks that are done by the job tracker to partition the intermediate key space. In the shuffle and sort phase, the intermediate data or the intermediate key space is copied over in a network. The MapReduce job with M mappers and R reducers, this means that you can have up to M cross R distinct copy operations. The reduce computation cannot start until all the mappers have finished. And at this point, I want to mention that we've already talked about stragglers and the fact that if there is a straggler in the map environment, the job tracker can spawn a new task in the back end, and if the new task finishes first, then its result is considered and the rest of the jobs then move forward. So straggling is specifically handled in the MapReduce environment. So once all the mappers have finished, and we also know there are no stragglers in the environment, it is important to emit the key value pairs, and all the intermediate key value pairs have to be shuffled and sorted so that they are sent to the appropriate reduce workers. Since the execution framework cannot otherwise guarantee that all values associated with the same key have been gathered. So here's an example and an illustration of the shuffle and sort operation. So here you will find that the map task is being executed. So you have a map key value pair which generates a set of intermediate keys. This is what is known as the mapper output. This mapper output will be written, we know, to the mapper local disk. But before it gets written to the disk, it's usually sorted. Now consider this scenario. You have data node 1, data node 2, up to data node n for your tasks. Each map task will generate these intermediate key spaces, and these will be sorted, but they will be written to the local disk. The shuffle and sort operation will actually do a further sorting of all the intermediate key spaces before it gets sent to the reducer. So here what you see in this column is the shuffle operation and the sorting of the intermediate key space. Now this is done specifically by what is known as a partitioner in the Hadoop environment. Once the partitioner finishes its job, the job tracker will then take this input and further send it to the reducers to come up with the reduce operation. So here you see that the input from the partitioner is actually sent to the reduce task, which then writes the answer to the DFS, as we have all seen before. So therefore, partitioners are specifically involved in the shuffle and sort operation. They are used to sort the intermediate key value pairs that come from the mappers. So the handoff phase of the shuffle and sort operation, the data from the mapper tasks is prepared and moved to nodes where the reducer will be run. When the mapper task is complete, the results are sorted by key, partitioned if there are multiple reducers, and then written to disk. To speed up the overall MapReduce process, data is immediately moved to the reduce tasks nodes to avoid a flood of network activity when the final mapper task finishes its work. This transfer happens while the mapper task is running, as the outputs of each record are stored in the memory of a waiting reducer task. And this is of course configurable. So partitioners are responsible for dividing up the intermediate key space and assigning intermediate key value pairs to the reducers. The simplest partitioner computes the hash value of the key and then takes the mod of that value with the number of reducers. This assigns approximately the same number of keys to each reducer. While this is a good mechanism of designing a simple partitioner, the disadvantage is that even partitioning of the key space occurs, but the values are not taken into consideration. A roughly even partitioning of the key space may nevertheless yield large differences in the number of key value pairs sent to each reducer. Remember, when we did the uh, quad protocol, we also said something similar, that while it helps to balance things out by hashing, there may be cases when um, a certain number is the files get hashed to a certain number more than to other numbers, and if this is the case, then there is not a very good load balancing. A similar situation occurs here. If the values are not taken into consideration, therefore the balancing that the partitioner does may not always be very good. The output from the mapper can be compressed as well to reduce communication overhead. Aside from compressing the output, you can potentially boost performance by running a combiner task. This simple tactic involves performing a local reduce operation for the individual mapper tasks. Okay, at this point, we've talked a little bit about the partitioners. I want to tell you a little bit more about what is the function of a combiner in the MapReduce environment. For this, we will have to go back to our favorite word count program. So given a text file which has a few sentences, our goal is to calculate the occurrence of every word in that file. So for instance, if you have two sentences, as follows, the sun rises in the east and um, the rain has not stopped. Um, in this case, the will appear first from the first sentence, that is, the sun rises in the east, and therefore you will have a key value pair, the, comma, 1. And in the second sentence, when the rain has not stopped yet, you will have another occurrence of the word the. Ideally, if there are no combiners in a MapReduce, in a mapper environment, you will find that the, comma, 1 will appear twice in your mapper output. This essentially means that every the, comma, 1 will then need to be sent to a partitioner, and the partitioner will then forward it to the reducer. This is what we've actually seen so far. This all sounds very good, except that the communication overload is the communication gets substantially harder. You may expect more bottlenecks in the network, and this is primarily because the, comma, 1 will have multiple occurrences. So, in order to avoid such a waste of communication bandwidth, what has been suggested is to design combiners, which are often termed as mini reducers, which take place on the output of the mapper. So if the mapper sees that there are two occurrences of the word the, it will have the ability to perform what is known as a reduce operation on its output before sending it to the reducer. So in other words, the combiner will now look for the occurrence of two the's and come up with the two and send only one tuple corresponding to the word the to the partitioner and then to the reducer. So each combiner operates in isolation and therefore does not have access to intermediate output from the other mappers. The combiner is provided keys and values associated with each key, the same types as the mapper outputs the key value pairs. So in this case, in this figure, you will see that this partition A alpha is sent to this mapper, and then this is broken down into A11, B22, and the combiner does nothing but just sends A1 and B2. This one, however, in the mapper sees C3 and C6, and this is combined together in the combiner to produce C9, which is then sent to the partitioner. So there is a local reduction phase that occurs inside the mapper. Then in the shuffle and sort phase, you basically aggregate everything. So you know that A sums up to 1 plus 5, which is 6. And so you have that 1 and 5 there. And B, as there are 2 occurrences from this mapper and 7 from this other one. So this should yield be sent to the reducer, and this will then perform the total count. Similarly, C is seen to have 9, 2, and 8, which are being stored as the output of the shuffle and sort phase. So this is how the combiners work in Yarn inside each of the node managers. Remember, the node manager was the one's thread manager which runs on each node in the Yarn environment. The node managers essentially allow the containers to have their application management being done, and but the resource manager is the one that controls each of these node managers. The node managers themselves will be executing the combiner, and the combiner in the MapReduce environment does support optimization. Um, it operates in isolation and therefore does not have values associated with each key. Critically, one cannot assume that a combiner will have the opportunity to process all the values associated with the same key. Now, should the combiner be written once or multiple times? Can performance of the system degrade if there are multiple combiners in the system? That's for you to think a little bit and see if you can figure out an answer. That's all I wanted to cover in this special video lecture where we talk primarily about the partitioners and combiners. Hopefully this should bring you to the end of chapter 2 of your MapReduce book. Next class, which will be on Monday, I will get started with chapter 3 of the MapReduce book. Thank you.